In this example, we're asked to simply set up but do not evaluate the double integral. We'll begin by graphing the two-dimensional domain region and then use that graph to determine the order of integration. So the domain region is a triangular region that's bounded by the ordered pairs 0, 0, 1, 2, and 0, 3. And so here's our triangular domain region. Let's think about our options. If we were to take a little tiny rectangle and start by floating it to the left and to the right, this would be integrating with respect to x first. If we have that rectangle down in this lower region, we have a leftmost boundary that is the y-axis and a right boundary that is a line, but we end up with a different right boundary if our rectangle is in this upper region up here. We have the same leftmost boundary throughout, but the boundary on the right is going to change. Now this scenario is possible to work with, but we would need to set up two separate integrals and add them together. Before we take a look at what that would look like, let's consider integrating with respect to y first. If we integrate with respect to y first, our rectangle would be floating up and down. We would have a lower limit that is this bottom line and an upper limit that's the top line, and those limits are going to be the same no matter where my rectangle is in this region. So if we integrate with respect to y, it's actually a little bit more clean. So if we integrate with respect to y first, we are going to have varying limits of integration in our innermost iteration, and these limits are going to contain x variables. And that's okay because when I integrate with respect to y, the x's are being held constant. Now to determine what those limits actually are, we need to find the line equation that is this lower limit and the line equation that is the upper limit. The line equation for the lower limit is going to be y is equal to 2x, and the line equation for the upper limit is going to be y is equal to negative x plus 3. So since x variables are okay in these limits of integration, we'll say the lower limit is going to be the equation 2x, and the upper limit is going to be negative x plus 3. Now we need to think about the limits with respect to x. So this is determined by envisioning the extreme locations of the bands that we're adding up. So when our band is as farthest to the left, the value of x in that case is going to be at 0. So 0 is our lower limit. And when our band is in this extreme location on the right, the value of x is positive 1, so that's going to be our upper limit. And since we were asked to set up but not evaluate, we would be finished with this portion of the problem. And this was the scenario where we integrated with respect to y first. Now let's go back and consider how we might proceed if we wanted to integrate with respect to x first. Again, if we float left and right with respect to x first, we have a different lower limit and upper limit in this bottom region than we would in the upper region. But that is something that we can work with. We would just need to split this domain region into two distinct areas and create two separate integrands and then add them together. Let's begin by looking at this lower region, and we'll create a double integral. 2xy is the integrand, and this time we want to integrate with respect to x first and then with respect to y. So focusing on this first region, the lower limit is this leftmost boundary, and with respect to x, that's going to be the constant value x. The upper limit is going to be a changing quantity, but we have to solve this equation for x in terms of y, because these inside limits of integration cannot have the variable of integration within them. In other words, we can't have x's in the limits if we're integrating with respect to x. But we can have y variables, so we just need to take this rightmost boundary equation and solve it for x in terms of y. So our upper limit would then be y over 2. Now, to get the y limits for this lower region down here, we're going to envision our band at this lowest extreme, and down here the lowest value of y is going to be 0, and when our band is at its uppermost extreme, the highest value of y is going to be 2. Again, we're only looking at this bottom region. Now, we're going to need to add to that the double integral that represents this upper region. And again, we're integrating with respect to x. The integrand remains the same. We're integrating with respect to x first and then with respect to y. Since we're integrating with respect to x first, we cannot have any x's in these limits of the inside iteration. So the lower limit up here is going to be x is equal to 0, but the upper limit, which was y is equal to negative x plus 3, we actually have to solve this for x in terms of y to get x is equal to 3 minus y, and that is what's going to be our upper limit. Again, when we're integrating with respect to x, it's okay to have y variables in those limits. Now in this uppermost region, we're going to envision where our rectangles are at their extremes and say when we float the bands then up and down, what are the minimum and maximum values of the y's? Well, at the lowest level, the minimum y value is going to be 2, and when our band is near the top, the maximum y value is going to be 3. So in order to integrate with respect to x first, we needed to split that region up into two separate areas because of the fact that the limits were not going to be the same throughout the entire region.